So this unit is a unit about translations. When we perform a translation, we often use what's called a vector. So you might remember Vector from Despicable Me. Vector was a villain, and he talked about himself as having both direction and magnitude in the committing of his crimes. A vector is a quantity that has direction and magnitude. When we say magnitude, we really just mean length or the size. And the direction, obviously, is the direction. We could talk about an angle like, 45 degrees northeast. Or in this case, we could give the direction by talking about how far horizontally we've moved in either direction or how far vertically we've moved in either direction. And the way that we represent a vector is we just draw an arrow, and we say that that arrow connects 2 points. So maybe point A over here and point B over here. And it has to have an arrow because the direction matters. In other words, AB is not the same vector as BA. Right? So if you think of it as a ray has an endpoint and moves along a certain path, right? But a ray is ending. This isn't like a ray, even though we have an arrow on one side. It is a line segment, but we put the arrow to indicate which direction we're moving. So this is a vector, right? It's got an initial point or a starting point. That's going to be point P. And it has a terminal point, so that's where the vector ends at point Q. The vector is named PQ. It's got a horizontal component. That's this part down here. And it has a vertical component, right? That's this part over here. So the component form of a vector shows both the horizontal and the vertical components, right? So if I want to write this vector in component form, I would write 5, 3, where 5 represents the horizontal. We put the horizontal first. And 3 represents the vertical change. And these pointy brackets, right, they need to be pointy. That's what indicates that this is a vector and not an ordered pair or part of a set or anything else like that. So example 1, name the vector and write it in component form. So first we would name this vector. Okay, so this is vector BK. Again, can we write this as vector KB? No, we can't, because we need to write the initial point first. So it has to be BK. Secondly, find the slope of the line segment KB. Okay, so now I'm calling this a line segment. Right, this vector is the vector -5, 2. All right, so what do we notice about the slope of the line segment? So remember, slope is rise over run. Really, rise and run are just the horizontal and the vertical components, right? This is the vertical. And this is the horizontal. And what I notice when I find the slope is that the slope is just giving me the ratio of the vertical component to the horizontal component. So now we're going to talk a little bit about transformations. So what is a transformation? It's a function that moves or changes a figure in some way to produce a new figure called an image. So this chapter, chapter 4, is all about transformations, and we're going to look at specifically 4 different transformations. So you can see these images on the right here. So one of those transformations is a rotation. You can spin things around. One of them is a reflection. So we can flip something, a mirror image of it over a line. And we can also look at translation. So a translation is basically just a slide. You're just sliding things around in the coordinate plane. So the other thing we want to talk about is what is the difference between the image and the pre-image. So the pre-image is the original figure. And then the image is the picture that we get after we change it in some way, right? So the image is the new figure. So when a transformation preserves length and angle measure, it's called a rigid motion. We're going to be primarily using the word isometry. Isometry. So what is an isometry? It's basically some change that you do to a shape, right? So you can see all these changes over here, a rotation, right? So this was the pre-image and this was the image. Does it seem like the pre-image and the image are identical in every way except for the orientation? Yes, so rotation will be an isometry. Let's look at the reflection. Here's the pre-image and here's the image. Does it seem like the pre-image and the image are exactly the same size and shape and the only thing that's different is the orientation? Yes. And lastly, the translation. Here's the pre-image and here's the image. Does it seem like the pre-image and the image are identical in every way except for their position in the coordinate plane? Yes. So translation is another type of isometry. So translations is what we're going to be talking about today, and then we'll look at the other transformations later in the chapter. A translation is an isometry, right? So remember what an isometry means. Isometry means that the pre-image will be congruent to, that means same size and shape, to the image. The pre-image will be congruent to the image. Okay, and a translation is going to map or move all of the points along some vector, right? Remember, the vector is going to describe the vertical and the horizontal movement. So in this case, it's telling us that this is going to be a horizontal shift of 4 spaces to the right. And it's telling us that it's going to be a vertical shift of 3 spaces down. So the translation is going to map the lines, okay, and they're all going to be parallel because it's all moving in the same direction. Okay, so we would notice that all of the lines that are moving the shape down are all parallel, and all of the lines moving the shape to the right are parallel, right? These guys. So let's take a look at this example. It says the vertices of triangle ABC are 0, 3, 2, 4, and 1, 0. So let's draw that. Boom, there's my triangle. And now I want to translate ABC using the vector -2, 3. So remembering that the vector is telling us how to move horizontally and how to move vertically. So it's telling us that every point should move left 2 and up 3. So one of the things that's easy to do if you didn't want to draw this is you could just take the vector and you could add the horizontal component, -2, to all of the x coordinates for all your points. And you could take the vertical component, 3, and you could add it to all the y coordinates of all your points. So if I write down points A, B, and C, add the vector -2, 3 to each of these ordered pairs, I can get the points for the image, right? So remember, this guy is the image. He's the shape I make after the transformation. And these guys are all the pre-image. They are the coordinates I had before I did a transformation. And when we add the vector to the original points, we end up with A prime, B prime, and C prime. As we map that, we get the blue triangle, and we notice that we shifted everything exactly as they told us to, right? We went 2 spaces to the left, and then we went 3 spaces up for each point, for A, for B, and for C. All right, let's look at another example. In this example, we're given a transformation or a translation, and we're asked to write the rule. So remember, the rule that we're going to write is going to tell us how much did we move vertically and how much did we move horizontally. So first thing to note is that this guy is your pre-image and this guy is your image. So we can draw some lines to show how much movement we've had, let's say like from point A to A prime. And once you draw these lines in, you can see that you've moved up 1, right? So that's the vertical component, and you've moved left 4, or -4 spaces. That's the horizontal component. And that means we can write this rule as the vector -4, 1. Okay, example 4. So let's graph a quadrilateral ABCD, and it has the following vertices. A is -1, 2, B is -1, 5, C is 4, 6, and D is 4, 2. This time, instead of giving us a vector to translate our shape, they're giving us mapping notation. So mapping notation is really giving a set of instructions just like a vector, but instead of telling us how to move X and how to move Y, they're just showing us how the point XY is going to transform. So the point XY is going to transform because X is going to be increased by 3 and Y is going to be decreased by 1. So another way of writing this, of course, would be the vector 3 to the right, -1, down 1. So now I can move all of my points 3 spaces to the right and down 1. Oops. Let's put those on there. So B is going to go 3 to the right, down 1. There's B prime. And C is going to go 3 to the right, down 1, C prime. A goes 3 to the right, down 1, A prime. D goes 3 to the right, down 1, D prime. And when I connect all of these, I find the image of my shape. Compositions. When 2 or more transformations are combined to form a single transformation, the result is called a composition of transformations. The composition of 2 or more isometric transformations is also isometric. In other words, if they both preserve the same size and shape, then even if I perform 2 compositions, it should preserve the same size and shape. So for instance, if I first translate this triangle, right, I move everything along this vector, that preserved the size and shape from the purple triangle to the blue triangle. But then you'll notice that in the next one, it looks as if I have reflected it over this line. A reflection is also isometric. So therefore, the change from purple triangle to the pink triangle is isometric. Okay, so let's look at last example. Graph RS with endpoints -8, 5 and -6, 8 and its image after the composition of the following 2 transformations. Now my graph's a little small and I'm not going to be able to graph the original points, R and S. But what I can do is I can see what it would look like to combine these 2 translations together. So when you have 2 translations, you can simply add those translations together. So a +5 and a -4 has a net movement of +1. And a y take away 2 and a y take away 2 has a net movement of y take away 4. In other words, 4 spaces down. So I know the resulting composition will move everything to the right 1 and everything down 4. So we also could have done this using vectors, right? And so what's going to happen is my point R, which was at the coordinate -8, 5, if I apply this transformation, 1 to the right, 4 down, will become the point -7, 1. And my point S, which had coordinates -8, -6, 8, if I apply the transformation 1 to the right, 4 down, will become -5, 4. And I can graph this guy on my coordinate plane. And that's what R prime, S prime, or the image of this composite translation looks like.